All right, as a chief systems engineer, I've seen my fair share of tough challenges in the auto industry. But today, we're diving into one of the big ones, one that's really defining the next wave of mobility. We're talking about how to build functionally safe micro-electric vehicles. This is our strategic briefing, the absolute core requirements for getting this right. So, it all boils down to this one question. How do you engineer a safe car for the price of a tablet? And look, this isn't just some clever thought experiment. This is the real-world engineering mission for what we call micro LSEVs, or low-speed electric vehicles. Every single choice we make, every component, every line of code, it all has to answer this question. You see, we're working under what I call a dual constraint. On one side, you have this absolutely extreme cost pressure. We're talking about using simple, industrial-grade components instead of the usual custom, fault-tolerant automotive stuff. That's the kind of cost saving we're dealing with. But on the other side, zero-tolerance safety rules. Regulators all over the world are getting tougher and tougher, especially on things like battery fires and electronics. So, the expensive, super redundant solutions from traditional cars, they just won't fly here. So our strategy can't just be to take old solutions and shrink them down. It doesn't work. We have to completely re-architect safety from the ground up. And we do this with two key ideas. First, risk-based tailoring, which basically means we focus our energy on the real-world risks these little vehicles actually face. And second, architectural decomposition. That's a fancy way of saying we build in safety through clever system design instead of just throwing expensive hardware at the problem. Okay, so let's get into why a one-size-fits-all approach is totally out of the question. Before you can understand our design choices, you really have to see the global landscape we're working in. And trust me, it's a complete maze of safety rules. What's fascinating here is just how fragmented everything is. I mean, look at this. In Europe, a vehicle is defined as an L6E quadricycle, which means it's strictly limited by its speed and power. But then you jump over to China, and their new standard is all about battery thermal runaway. That's when a bad cell overheats and starts a chain reaction. Their rule is simple and honestly brutal. No fire, no explosion. Meanwhile, Japan has these really high expectations carried over from their bigger cars, and the US has its own set of rules. We're not playing one game here, we're playing 4 different games at the same time. And this regulatory maze, it forces every single engineering team to a huge strategic fork in the road, right at the very beginning of a project. It is, without a doubt, the first and most critical decision we have to make. And this slide really lays out that fundamental choice. Do we stay under the 60-volt safety extra low voltage threshold? This is the 48-volt path. The big pro here is you slash costs because you get to avoid a whole bunch of complicated high-voltage safety rules. The catch? At 48 volts, the currents are massive, and that creates some serious thermal risks. Or do we go high voltage for better performance and fast charging and just accept the extra cost and complexity that comes along with it? Now, to really get the high voltage path, you have to understand HVIL. It stands for High Voltage Interlock Loop. The best way to think about it is like a continuous safety wire that's daisy-chained through every single high-voltage part in the car. It's like the safety bar on a roller coaster, right? If that bar isn't perfectly locked in place, the ride's not starting. It's the exact same idea. If any connector is even a little bit loose, that chain is broken and the system kills the power instantly. It is absolutely non-negotiable for anything over 60 volts. And yeah, it adds cost and complexity. So let's move on and look at how we tackle the 2 highest risk scenarios that come out of our hazard analysis. Both of these are rated at the highest possible level, what we call the Automotive Safety Integrity Level, or ASIL. And that means we have to engineer them with, well, extreme prejudice. Both unintended acceleration and battery fires, they're classified as ISIL D risks. In the world of functional safety, that's the top of the mountain. It means that any failure has the potential for fatal consequences. It demands the absolute most stringent, rigorous, and verifiable level of safety engineering. There is just zero room for error. And this brings us right back to our core problem. How do you achieve ASIL D-torque safety? Preventing the car from just taking off on its own without using those expensive multi-core lockstep microcontrollers. Those are the chips with basically 2 brains that are constantly checking each other's work. You find them in premium cars, but for us, the budget just isn't there. The answer is a really elegant, cost-effective architecture called e-gas monitoring. And this is a perfect example of that architectural decomposition I was talking about. We create safety with 3 independent layers that are all checking on each other. So level 1, that's the main processor doing its job. Level 2 is a totally separate, simple process that's just asking, hey, does that request even make sense? And Level 3 is a completely external hardware watchdog chip whose only job is to ask, is the main processor still alive and kicking? If the answer to any of those is no, the system is shut down safely. No single point of failure can cause a disaster. Okay, now for that second ASIL-D risk, battery safety. And let me tell you, the global benchmark here is no longer up for debate. It's being set by China's incredibly aggressive new standard. The goal isn't to give people 5 minutes to get out of a burning car anymore. The goal is to prevent the fire from ever happening in the first place. So, how on earth do we meet a challenge like that? Well, it takes a multi-layered defense. First, we mandate the safest cell chemistry out there, which is lithium iron phosphate, or LFP. Then we physically isolate the cells from each other using advanced thermal barriers, stuff like aerogel. We also design dedicated channels to vent any hot gases safely away from the battery pack. And finally, we use an ultra-precise battery management system that can detect the tiniest little voltage drops or temperature changes. Those are the earliest warning signs that a cell is in trouble, long before it becomes a catastrophe. But look, having the slickest architecture in the world is only half the battle. A truly safe vehicle can only be built by a team that lives and breathes a culture of safety, and that culture has to be backed up by seriously rigorous processes. This leads us to a principle that is completely non-negotiable. Safety cannot be compromised for deadlines or for budget, period. And this isn't just a nice idea, we enforce it in our structure. We require an independent safety manager who reports directly to the CTO, not the project manager. We make sure our engineers have formal training. And we use legally binding agreements, called DIAs, with every single supplier to make sure their parts meet our safety specs. It all gets documented in what we call the safety case. That's our complete book of evidence proving this vehicle is safe. So, we end right back where we started. In this global race for affordable mobility, where do you draw the line between cost and safety? What this explainer shows, I hope, is that the line isn't a compromise. It's actually a new frontier for innovation. It's all about designing safety to be smarter, not just more expensive. And that right there is both the incredible challenge and the massive opportunity in this micro EV revolution.